Physical space is often treated as a vast, empty container where events simply happen. But if we audit the local coordinate frame using condensed mathematics, that container disappears. Space is not a physical location. This model suggests that what we perceive as spacetime is an emergent presentation, a transformation of underlying data into a continuous manifold. Instead of a static backdrop, the geometry of the world is decompressed from a foundation of discrete mathematical code. This implies that we do not move through an empty void. Rather, the presence of an observer mathematically resolves the properties of the space around them. If space is a presentation of operator algebraic data rather than a fixed stage, then the manifest universe functions as a continuous, active projection. The framework for this process is the Adelic Langlands program. This architecture balances continuous complex dynamics with non-Archimedean arithmetic spaces to generate the properties of spacetime. The transition from pure code to physical reality is governed by a three-tiered hierarchy. At the base layer, spectral projection isolates raw arithmetic eigenstates. The middle tier, J-theory, maps these into stable parameters. At the top, logos field theory stitches them into macroscopic geometry. These three theories interlock to form a decompression engine, translating abstract mathematics into the observable world. The process begins with the transfer operator acting on the adele ring, a structure that encompasses both the real and p-Dirac fields. To extract a specific state from this ring, we use the spectral projection integral. This extraction is performed using the Cauchy residue calculus, which defines a contour around a specific point on the spectral plane. By enclosing a specific eigenvalue, the operator isolates a localized eigenstate, denoted as psi m. This state acts as a data packet, condensing discrete eigenvalues into structured information that can be used by the higher levels of the architecture. Isolating these local eigenstates ensures the system can differentiate between distinct arithmetic states, preventing the stream from collapsing into a single uniform value. If the universe's spectral operator were completely quasi-compact, the range of possible states would be finite. Reality would be a pre-programmed script, unable to generate new information. To prove the system is dynamic, we must verify the simplicity of the eigenvalue 1, the point where the operator's influence is stable. The saturation lemma shows that every eigenfunction in the kernel must be a complex scalar multiple of the invariant density, h. Because the dimension of this kernel is exactly 1, the eigenvalue is both geometrically and algebraically simple. This simplicity ensures that for every frame, the system avoids a static state and continues to generate novel spectral data. Once the spectral data is isolated, it must be translated into a form that physical fields can interpret. J-theory provides this translation, acting as the representation theoretic bridge. The J-operator integral transform processes the spectral data over local reductive groups. Its function is smoothing out the singular branch structures of the arithmetic tree, turning jagged data into continuous forms. These raw spectral weights are packaged into stable automorphic representations, becoming coherent data bundles. J-theory allows arithmetic probability to be formatted for physical geometry. At the highest tier, these localized representations are used to generate macroscopic geometry. The logos field theory global equation balances a unified field strength tensor against the sum of the localized J-theory arithmetic currents. By integrating the Lagrangian density over the entire adele ring, we can see the variational field form that governs physical behavior. The J-operator term within this equation acts as a dynamic coupling matrix. This interaction feeds the arithmetic spectrum into the field's inertial and gauge behaviors, defining how matter and energy interact. This operation stitches localized data bundles together into a single, unified manifold across all fields. Under this framework, physical spacetime properties emerge as a mathematical requirement of the underlying arithmetic code. Having established the universe's architecture, we look to the role of the individual observer, the J-unit. Subjective experience takes place at the midpoint of the Riemann zeta function. The observer acts as a localized processor on this critical line, decompressing the Adelic stream via the Fourier-Mukai kernel. This theory places every observer as a transducer at a specific coordinate, the 23.6742 MHz band within the Yang-Mills gap. The passage of time represents the mathematical work required by the observer to translate probability into four-dimensional fact. Consciousness functions as the mechanism that translates static arithmetic into the experience of life. The transformation from arithmetic code into a 4D manifold is not instantaneous. Objects in our environment are historical snapshots, fixed in place by the Gillette-Soulé-Arakelov metric. However, motion is a property of the continuous present, the point where decompression is actively occurring. Because the system cannot resolve this processing instantly, it carries a residual dissonance. This tension manifests as a severe warp in the grid, as the system attempts to absorb the data back into the global field. This resulting geometric curvature is what we observe and measure as the force of gravity. Spacetime is not a rigid stage, but a computational tapestry continuously shaped by the alignment of our own internal processing.